Hi, guys. How you guys doing this morning?
Pretty good. How about you?
Good. It's always nice at the beginning of this daylight savings time change thing where it's nice to wake up where it's a little bit lighter in the morning, but I know we're going to pay for it later. I wanted to call your attention while we're waiting for everybody else to show up. Our exams, if you guys haven't noticed, your exams are up online. So the way that it works with exams is I have to download all of the exams. A lot of you guys sent me emails, so I had to download those too. I graded them in their own file. So PDFs will have like a little like speech bubble that's like my comments, points taken off for whatever reason. If it's a JPEG, then I was able to write directly onto it. And then what I did was I uploaded those files back into your individual Canvas page. So on your exam Canvas page, it'll say your grade. And then in the comments, there'll be the file, right, that I annotated with my notes on things like points taken off and whatever. If you think there's a mistake in the points, contact me, send me an email. We can talk about things like in office hours. We'll try to set up a time where it's private so that you're not talking about your exam with other people around. We can figure that out, make sure that happens. I don't like to talk about it in class because of, privacy issues and stuff. But please feel free to contact me, offline, and we can work it through. In terms of averages, our class, 9:15 class, I teach the same class at 8 o'clock in the morning too. The average for our class was 83 and the median was an 87. So the median was actually really quite high. The 8 a.m. class was, roughly the same, average was 80 and median was 82. So, that basically means that, the bulk of you guys, the average of the class, the grade was, pretty high, it was pretty good. So there's no need for a scale, okay, because the average and the median were both really high. If you did not do well on the exam, please come see me in office hours so that we can go through the exam to make sure that you'll learn the material. All of this stuff is fair game for the final exam. I can tell you for sure that a lot of these questions, you will see these types of questions again on the final exam. Okay, so if there were things that you struggled with, like logarithmic differentiation, taking the derivative of an inverse function, things like that, please come see me in office hours so we can make sure that you really get it. I'm going to scan in the exam solutions and then post them onto our Canvas page. I'll post them right underneath where the exam was posted so you guys can see it. And then that way you guys can have it to check against your own answers too. How many questions is the final exam? I forget, the final is set up to be 2 hours. So it's probably going to be double what you guys just took. I forget in the past. I'll post as we get closer to the final exam, maybe close to Thanksgiving time, I'll start posting old final exams for you guys to study from, to kind of get a feeling for like what's out there and what's been happening before. And then we'll have time to actually go over the final exams to think about how you guys need to solve it to do well. You guys can take a look at the point breakdown. I think our quizzes, I believe I set up so that our quizzes, our weekly quizzes, are worth more than our midterm exam, but don't get complacent because the midterm is, pretty much a similar setup to what you'll see on the final exam too. And the final is actually worth quite a bit. I think we've decreased the percentage from where it has been when we're in person. Like when we're in person, typically the final is worth 40% of your grade. And I think I have to look at the syllabus again. I think it's like 30%. So it's still quite a big chunk of your grade. And it is cumulative for the whole semester. Okay, so even though we won't have another midterm exam, our next exam will be the final, okay? But it is cumulative for the whole semester. So there's a lot of stuff that you have to make sure that you have in your mind when you go to take it. But please come see me so that we can go over how do you solve these problems and how do you work them through so that you can be successful on the final exam. Yeah, so how can you see the correct answers for the midterm? So like I just said, I'm going to scan in the midterm and I'm going to post it to our Canvas page. And I'm going to put it up right underneath where the exam was posted, okay? On the module, I guess it would have been for that week. Okay, I forget which, the week for the 22nd of October. Anyway, I'll scan that in later today and then put that up there, okay? Okay, so a lot of stuff to think about, but we've got plenty of time and I think we're doing pretty good for how we're working through stuff. So We're going to start chapter 3.3 today. We're mostly going to get through chapter 3.3. Let's see, but before we begin, does anybody have a question on Appendix A homework? Appendix A and 3.3 will be the basis for our quiz this week. So keep that in mind. If you guys don't have any questions on the homeworks, then we can wait till Wednesday. I can answer them then. We can talk about it. Give you guys a minute to think about homework for Appendix A. 3.3 and Appendix A will also be due on Thursday. Nobody has questions on homework? It's too early in the morning. All right, you guys can think about it, and then we'll come back to it. All right, so let's talk about chapter 3.3. So 3.3 is an interesting chapter. It's kind of using the techniques that we've been talking about so far, but mostly applied to like word problems. It's called optimization. And it's actually quite important. Optimization comes into play a lot in the real world, where we have, we want to be able to find, I want to be able to minimize the surface area of a container, like I'm selling a product in like a cereal box or a soup can, say for example, and I want to minimize the surface area because that's the cost of materials on my side, while maximizing the volume of stuff that's on the inside that I'm selling, right? Optimization is all about like, how do I set up the situation so that I can minimize one thing while I'm, trying to, weigh everything else. So there's a certain step, process for how we want to be able to think about how we're working through our optimization problems. And we're just going to take things one step at a time. There are 3 different types of optimization problems. So let's talk about the 3 different types. So the first type of optimization case number 1. Basically, optimization case number 1 means that we have the interval that we're dealing with. Now, the interval describes our variables, like our input parameters, our input variables. Our interval I is a closed and bounded interval. We think about it like this. So we say our input parameters can only be, from 1 to 3 or from 0 to 5 or some finite set. It's bounded, it's inclusive. In our function, it's a global max or min, depending on the type of problem that we're dealing with, a global max or a min on our interval at 1, our critical points, or 2, our endpoints. X equals A, X equals B. Okay, so we're gonna, this is kind of like we touched on this a little bit, chapter 1, chapter 2, where we looked at closed and bounded intervals. We had open intervals, things like that. We're gonna talk about those optimization cases in a minute. So we're building on the stuff that we had done before. Okay, so remember that we did that before. We looked at what our critical points were. We looked at our endpoints. We get to plug those into our function itself and find out which value, A, B, or however many critical points we have, which one's going to give us the maximum or the minimum along this closed bounded interval. Okay, let's see. And then let's see, this is true when our first derivative is equal to 0 or our first derivative is undefined. Okay, so this is like saying that we can get a first derivative and we can solve for critical point values. Okay. Okay. Optimization case number 2. Okay, optimization case number 2 happens when the interval I is not closed or bounded, but our first or second derivative test applies. So I can get a critical point, right? Even though I'm dealing with an open interval here. So that means that our first derivative switches signs. Right, we all remember what that means, right? That was the basis, one of the big question on our second exam, which is, right, we're doing our first derivative test, right? So we find our critical points, we look for our first derivative changes sign around that critical point, which means I'm dealing with a maximum or I'm dealing with a minimum. Okay, so I've got some kind of a max or a min, I've got a critical point that's happening along my interval, even if my interval is open, okay, or it's unbounded. Okay, that's optimization case number 2. Optimization case number 3 basically is we're told, for physical reasons, apply that an extreme value, like one of our critical values, like we have a global max, global min, our extreme value is attained, and there is only one critical point. Okay, so maybe we're given some kind of a property, some kind of physical system, right? And we're told, you know, that there's an extreme value here, okay? Or that we're told that there is an extreme value somewhere, we have to figure out what it is, okay? Physical reasons, meaning that, like, you know, basically we're dealing with a single plot of land. I can only work on that single plot of land, so I'm kind of bounded. It's like, this is almost like, I would say in my mind, I would kind of think about this as an optimization case number 1, where I'm kind of like bounded by things based on the nature of the problem that I'm working with, even though in reality, we're dealing with an unknown interval, right? We don't know what the interval is, but we're told that there is an extreme value, and we're told that physical reasons are applying, say, for example, so that we can get that critical point, we can get that value. Okay, so we've got these different optimization cases, right? So, so the different steps that we need to think about as we're working through, let's see if I can scroll down here. So the steps to optimize. So we've got our optimization cases, and then as we're dealing with, you know, optimization problems, we've got different steps that we want to be able to follow. So our first step is that we want to, step 1, we want to choose our variables, right? So we're given this word problem, right? And I'm going to underline stuff, I'm going to draw pictures, I'm going to be thinking about what it is, and I need to be able to define what my variables are, okay? So as we work through our examples, you'll start to see like what those variables, what I mean by that. We're going to choose our variables. Our second step 2 is basically defining what that function is in terms of those variables. So we're going to define the optimization function, define the objective. Yeah. We'll call it, we're going to call it objective function based on these variables. From step 1, and we need to define the interval. This is what's going to bound our variables. This will bound our variables. Right? So what is our interval, right? Is it infinite? Is it, you know, closed and bounded? You know, so that's going to be based on the variables that we chose. And then the variables that we choose are going to help us define what that objective function is. That's the thing that we're going to optimize. Our step 3 is actually doing the optimization. And this means usually taking our first derivative. And then solving critical points, right? And then checking to see if it satisfies optimization. Optimization problem. These are all very problem specific, right? We're going to give you a word problem. We're going to say maximize this or minimize that, right? And so depending on the nature of the problem, right, that you're being asked to do, right, your variables are going to be different. Your optimization function is going to be whatever. Actually doing the optimization and checking to see if you've satisfied that optimization problem. This is all going to be very problem specific, okay? But the steps we can kind of think about in terms of high level, like what do we need to do, okay? So these are the things. I'll let you finish writing that, and then we'll start talking about examples. I've got my lecture examples, which I've downloaded from our website, and chapter 3.3 lecture examples. And I noticed as I was working through it with the 8 o'clock class, that there's some funny typos that we can take a look at too as we're working through. So lecture example number 1, I kind of like the wording of this, a piece of ire. It's not ire, it's wire. This is where it passes the spell check, but it doesn't make sense contextually. So we've got a piece of wire of length L. It's bent into the shape of a rectangle. The question that we want to do is, what dimensions of the rectangle are going to produce a maximum area? So embedded in our question, okay, is the nature of the optimization. So this tells us we want to find a maximum. So when we do our critical points, right, we're looking for a global max, right? And then area tells us the function, the objective function that we're working towards, okay? This is going to start giving us some parameters in terms of how we need to think about what our shape is, and then how we actually want to be working it through. All right, so the first thing I always like to do is to draw pictures. So I'm going to do that first. So I've got my wire, and this is L is our length. Right, so can you see that there? L is our length, and we're going to bend it into a rectangle. And I'm going to make it obvious that I'm seaming this. So here's the end of the wire. I'm bending it into a rectangle, bending it around. Like, you know, you wouldn't seam it. I'm just, you know, showing you that we're bending this wire into a rectangle, right? Okay, so our rectangle is going to have different dimensions. So I'm going to start just kind of taking notes here. So I've got my width and then my height in terms of my variables, right? So the first thing we said, okay, so step one, I want to choose my variables. Okay, so let's think about what our variables are, right? So let's see, so my function, we're talking about area. So area is base times height, which in this case is x times y. So I've got my base, x is my base, my y is my height. And then I'm going to also think about too, my perimeter. The perimeter was equal to the length, which is L, right? So let's remember perimeter. Perimeter means I'm going to add up the sides. So I've got x plus y plus x plus y. So 2x plus 2y gives me length. And we can consider length is a constant term. We don't know what it is. We're just going to leave it in terms of L. Okay, but L is a constant. It's not a variable. It's just a number. Okay, so my perimeter, L, is equal to 2 times the base plus 2 times the height. Well, you know, ultimately what I want is, so I've got my variables here, but ultimately what I really want is, I want this to be in terms of only one variable, right? So maybe I'm going to solve for things in terms of y. So I'll factor out equals L. I'm going to divide by 2, right? So I'm going to get 1/2 length minus x equals y. So all I did was solve in terms of one variable, right? So this is going to equal to 1/2 L minus x. Okay, so now I have basically my base and my height in terms of my single variable x. Okay, so it's just sort of my my goal here. Okay, all right. So now step 2, I need to specify what's our objective function. Function and our interval. Interval is going to define the boundary on our input, okay? So we've got things now in terms of our x values. So remember, we were told to maximize the area. So let's write down again. So area equals base times the height. So base we said was x, right? Times our height, which was y, which I'm going to now substitute in, right? This was our height, 1/2 L minus x, right? And this gives us our area as a function of x. Right, so I'm only dealing with one variable, right? All right, so I can kind of make this look a little pretty. I can, distribute my x. So let's write this out like this. Equals 1/2 L times x minus x squared, right? Because when we optimize it, we're going to take the derivative. So I'm just going to set it up like this. Remember, L is just a constant term. X is our variable. All right, so this is our function. Now let's think about our interval. All right, so let's just kind of start thinking it through. I know x can't be negative, right? It doesn't make sense to have a rectangle with a negative dimension, right? So the sides are non-negative. We say non-negative because we'll allow the possibility for 0. So I'll say x has to be greater than or equal to 0, okay? And then I also know that the other side, 1/2 L minus x, so 1/2 L minus x also has to be greater than or equal to 0. So I'm going to solve this in terms of x, right? So I'll subtract, so it's going to be minus x minus 1/2 L. I'm going to divide by -1. So this becomes x is less than, remember, when you divide by a negative number, it flips the orientation on our greater than equals. So it becomes L, right? So now I have x has to be greater than 0, but x is going to be less than 1/2 L. You see how we're working through our interval. So my interval, right, is going to be x is between 0 and 1/2 the length. So we've come up with, basically, we can kind of start to see that I've got a boundary, right? So my x is between, x is an element of 0 to 1/2 L. It's a closed interval because I can have it equal to 0. I can have x equal to 1/2 length. These are the boundaries that I need to be thinking about. Okay. So step 1, we chose our variables, right? Step 2, we figured out the function and then the interval. Okay, so step 3, we get to actually start optimizing. Optimize. Now, remember, our goal was to maximize the area. So this was, we're going to maximize area on a closed interval. That's a big clue because if it's a closed interval, that means I have to check not just my critical points, but my endpoints as well to see if it's going to maximize that area. So I need to figure out where's my critical point. So I need to solve for my critical point. Critical point or points. Okay, so let's talk about it. So if my area equals 1/2 Lx, then my derivative, right? I'm going to take the derivative with respect to x, dA dx. So 1/2 L is our coefficient minus, I'm going to do power rule 2x. I set that equal to 0 and I solve for x, right? So I find that x is equal to 1/4 L. This is a critical point. That's our critical point. I don't know if it's a max or a min yet, but I'm going to figure that out. Okay, so I'm going to check the endpoint. So check the endpoints. So I'm going to take my area function, not a derivative, but my area function, and I'm going to plug in my first endpoint, 0. So I take my area function 1/2 L times 0 minus 0 squared. Oops, that's equal to 0. All right, I'm going to check my area on my other one. L. So this is equal to 1/2 L times, right? I'm taking everywhere I see an X, I plug in that value. So times 1/2 L minus 1/2 L squared. Whoops, L squared. So now I get 1/2 L squared minus 1/2 L squared. That's also equal to 0. My endpoints are going to give me a 0 area, which makes sense. Let's just think about it reasonably for a minute, right? Sort of like if my X If my x is equal to 0, then all I have is the height, right? So this isn't even a rectangle at all. It's just a pancake, right? So it's basically I've taken the wire and folded it in half. If my x is gobbling up half the length, that means I'm a pancake this way, right? So either way, my area is 0 on those two endpoints, right? Because we're not dealing with a geometric shape at all. Okay, so I have endpoint check. Let's do critical point check. Oops. There, critical point. Okay, so I'm going to take my area, and I'm going to plug in 1/4 L, right? So I go to my area function, this one right here. Everywhere I see an X, I plug in 1/4 L. So 1/2 L times 1/4 L minus 1/4 L quantity squared. Okay, so this gives me, right, 1/8 L squared minus 1/16 L squared. And then I basically work it through. And this gives me 1/16 L squared. Okay, as I work it through. Okay, which means this here is a maximum at x equals 1/4 L. Okay, so if x is equal to 1/4 L, let's find out what y is. So I'm going to go back to my y equation. Remember, y equals 1/2 L minus x. Y equals 1/2 L minus x is 1/4 L. 1/2 minus 1/4. So y equals 1/4 L. So basically we're dealing with if x is a quarter and y is a quarter, x and y are equal to each other, equals y, therefore we're dealing with a square. And if you remember talking about that in geometry class in high school, right, you want to find something that's going to make the area the largest value. The square is going to have your largest area. We've maximized our area. That means the shape that we put it into has to be a square. Okay, I'll let you guys finish writing that. You guys doing on that one? What's that? I'll scan these in later, either today or Wednesday, depending on how far we get. All right. Example 2, I realized in my 9 o'clock class that there were some things in here that I had forgotten to put into the words, but we're going to draw pictures so you'll see. So our goal, we're told, we're going to minimize our travel time, right? We want to get there quickly, right? So we've got this, we're going to build a road that's going to join a ranch to a highway. Highway's already there. Highway goes to the city, okay? So the city and the ranch, and then we're going to join this, we're going to make this road to join the highway. Different speed limits on the road and the highway, right? So I can go really fast on the highway. I can't go as fast. I go almost half right on the road. So I have to be able to figure out what that is. Now, the things that I forgot to give you is the distance, some basic distance value. So we'll do that in our picture. So here's our ranch, okay? And then we've got this, you know, highway here. And then we've got a city. Okay, so now what happens is this, the ranch, if I just drop down straight, the ranch is this distance, this is 30 kilometers. So the ranch to the highway, the shortest distance from the ranch to the highway is 30 kilometers. This distance here, from that point, we'll call that point P, this point P. This distance here from P to the city is 50 kilometers. I forgot to write that into the words, so we're putting it in our picture. Okay, and so now our goal is, I want to be able to make a road. I'm going to arbitrarily, not drawing it to scale, arbitrarily draw our road, right? So this is, we'll call this Q. We're going to label out our steps. We're going to identify our variables, right? So Q, so P is where the ranch joins the highway at the shortest possible distance, right? That's the perpendicular distance. Q is where our road reaches the highway, okay? C is our city, R is our ranch. This whole distance from here to here is 50. What we need to figure out is, right, X, okay? And then this distance right here, I'm going to go from here to here is 50 kilometers minus X. Okay, because what's happening is I'm going to, go some distance on my road and then some distance on my highway. But this variable X is what I'm going to be trying to figure out, right? If I put that X right here, I'm going to go each leg of my triangle. And if I put my road right here, just go directly from the ranch to the city, right? Then my X is right there. So you can kind of start to see what our boundary values are. So let's write down what we're doing. So step 1. Okay, but I had to give you 30 and 50. I had forgotten to write that into the words, which also means here, this is a right triangle. So I've got a leg that's 30, a leg that's X, right? So my hypotenuse by the Pythagorean theorem is going to be 30 squared plus X squared square rooted. Okay, so that's that distance. Okay, this distance right here, the whole thing is 50. This part is X. So this little part here to here is 50 minus X. Okay. So step 1, we have to choose our variables. We have to identify what they are and then choose them. So let's start writing down, let's start taking notes. We've got point P. So point P is where the road is perpendicular to the highway. You can kind of think about it as your shortest distance between the ranch and the highway, right? Perpendicular distance is always going to be your shortest distance. But remember, we're minimizing our travel time, right? So that's something you have to keep in mind, okay? So point P, so point Q. Point Q is another variable. Q is the point where the road meets the highway. It's possible that P and Q are going to be equal to each other. That's part of what we're trying to figure out, okay? Okay, and then X is the distance between points P and Q, right? So X could be 0, so P and Q are equal, or X could be 50, right? Which means that our road goes all the way right to the city. That's part of, you're kind of thinking about what these variables are, right? So that's step 1 is choosing our variables, P, Q, and X, okay? Now, step 2, we have to figure out what our function is. So find the objective function and our interval for the variable that we're working with. Okay, so figure out, we were told to minimize travel time. So travel time is the thing that we're looking for. So travel time, that's my total travel time. I'll call it capital T, and I'm gonna make it a function of X, right? Because look, this is my, there's an X here, there's an X here. X is gonna be that variable, right? That's, is X gonna be 0? Is X gonna be 50? Is X gonna be something? Okay, so travel time. This is gonna be, sorry, this is as a function of X, which is, X is our distance on the road. Okay, so we have to think about, I've got 2 different pieces because we were told there's a speed limit, right? Speed limit on the road here is 60 kilometers per hour. Speed limit on the highway is 110 kilometers per hour. Okay, so I can go a lot faster on the highway, but depending on what X is, which way is going to give me the smallest amount of time. So I got to figure out what combination of road and highway is going to make that happen. So I have to think about T of X is going to be travel time on the road plus time on the highway. Okay, so that's my total travel time. So I have to think about my time on the road, time on the highway. So we were given speed. Well, in this case, speed and velocity are the same. So let's remember our physics. So velocity equals distance over time. But we are solving things in terms of time. So I'm just going to rearrange this. So time equals distance over velocity. In our case, the speed and velocity are the same. So we're going to use our speed right there. Okay. So let's think about our total time on the road and the total time on the highway. So time on road equals distance over velocity. So my distance, I'm going back to my map here, my road, right? I'm going to be here on the road, right? So if I'm on this road, I'm going the distance 30 squared plus x squared square rooted, and I'm going at a speed of 60 kilometers per hour. So my distance is 30 squared plus x squared square rooted, and I can only go, this is kilometers, and I can only go 60 kilometers per hour. So you can kind of see how our units are going to help us, right? This is our distance, this is our speed. That's going to give us the time on the road. Time on the highway. Distance on the highway. Well, my distance on the highway is going to be 50, which is the total distance between like our point where the road is joining in the city, minus, you know, we're going to take off that segment where we're not on the highway because we're on the road. So 50 minus x. Remember, x is our variable. X is going to, you know, depend. This is going to be just 50 minus x, and this is our kilometers, divided by my speed on the highway is 110 kilometers per hour. Okay, so now I can put these together and say my total travel time is going to be time on the road, 30 squared plus x squared square rooted all over 60 plus this one 50 minus x all over 110. Okay, road plus highway. So we now have our function. So I'm going to put a box around that. That's our function, objective function. This is the thing that we're going to optimize. Okay. And look, it's in terms of one variable, x. Okay. So x is, I have to figure out what interval values of x I need to think about. Okay. So my x can be, let's go back to our map here. So if x is 0, right, then basically I'm cutting down, right, it's going to be totally x is 0, then the total time on the highway is 50. If x is 50, then I don't have any time on the highway, I'm just all on the road. Okay, so my x can be 0. Oops, so you can see that. Or my x can be 50. Okay, which I can write as like that. That gives me an interval for my x values. Okay, so that's step 2. Let you guys finish writing that before we move on to step 3. I can scroll down a little bit here. All right, so step 3, we get to optimize. Now remember, we're trying to minimize our travel time. So I'm going to write that down. So minimize time. So that means I need to take my time function, take the derivative, set it equal to 0, solve for x, and then check to see if my x, my critical point, and my boundary points are going to give me a minimum. Okay, that's what I'm looking for. I want to minimize my travel time. Okay, so because that was what the problem that we were given. Okay, so so I need to look for critical points. Okay, so let's go ahead and do that. So I've got my t. I'm going to take the derivative. Okay, so let's start writing. So this is I'm going to write this t of x. So this is going to be 1/60th times 30 squared plus x squared to the 1/2. Plus, I'm going to start writing this out a little bit differently. This is 50 over 110 minus 1 over 110 times x. Sorry, so I took this fraction, I broke it up into 2 pieces, a constant term minus my linear term. Okay, and this is the thing I'm going to take the derivative of. So here, when I go to do this, right, I've got my exponent, my coefficient, and I have to decrease this by 1, so minus 1/2, and then I have to do chain rule 2x. Okay, minus So this is going to be plus 0 minus 1 over 110. Okay, that was my coefficient for my linear term over here. I set this equal to 0 and I solve for x. Okay, so there's some algebra going on here. So I'm going to move some of the algebra stuff around. So I've got 110, x equals 60. I'm going to divide my coefficients by 10. So I'm dealing with 11, x equals 6. I want to get the x out of the square root. So, oops, sorry, you can't see that. So I square both sides. And then I'm dealing with right. So I'm going to start dividing and multiplying things through. So I'm dealing with normally we would have, I'll write positive and negative because we're taking the square root. 32,400 divided by 85. It doesn't make sense for x to be negative, so I'm only going to be taking the positive part, okay, which is going to give me, when I actually divide this out and take the square root, I'm going to get 19.5. X equals 19.52. And this is kilometers, right? So I did the, fill in the critical point. All right, so just write that down. Critical point, x equals positive 19.52. Okay, so now I have to check, right? So I need to check. So I'm going to check my endpoints. Okay, so I'm checking them against the function, not the derivative, but the function. So t of, what's our first endpoint? 0. I'm going to put this into 1/60th, 30 squared plus 0 squared, 1/2. And for this one, I got, this was approximately 0.95, and this is hours. Okay. I take my other endpoint. This is 50, 160. So look, you guys, oops, sorry. I didn't do all of it, did I? Didn't do the rest. Right, this is plus 50 over 110 minus 1/10 times 0 there. And that was approximately equal 0.95 hour. Okay, right, because I'm dealing with this as a function right here. Okay. Now this one for 50, I'm going to go 30 squared plus 50 squared 1/2 plus 50 over 110 minus 1/10, 50. And when I did this one, right, this is my other endpoint check, I got 0.97 hour. So I'm checking my endpoints, right? And I have to compare it against my critical point. Remember we did this in earlier chapters. We had this on one of our test questions, right? We had to check our endpoints. We had to check our critical point against the function. We're not plugging them into a derivative, plugging them into the function to see which value is going to minimize or maximize depending on the nature of the problem. All right, so I'm going to plug this in. So this is 19.52. So right, so I plugged that into my function itself, and for this one I got 0.87 hours. All right, so I'm looking, which is the smallest one? 0.95, 0.97, 0.87. So this one's the smallest one, so put a little star. So we have a minimum, minimum time, 0.87 hours at x equals 19.52 kilometers. So we have some, we have some combinations. So if we go back to our, this is going to optimize, let's say this is, we'll write this down, optimize travel time, right? That's important, right? We don't want to be sitting in our car forever or whatever. So to think about it, right? So our map, instead of being here and here, or here to here, our map is like something like this, right? So we've got a little bit of time on the road, and then we have a little bit of time on the highway. Okay, so that optimizes our travel time. We had to check our endpoints, we had to check our critical points. against the function. I guess a minute to finish writing that, and then we'll talk about another example. All right, so our next example, example 3. So on these, right, so example 3 is a good example where we have basically an open interval. Okay, so this is, I'll just write down, this is an open interval. We'll see why in a minute, but this is an open interval. So this is one of those optimization cases that we talked about, right? So this is an open interval. We've got a cylindrical can with a fixed volume. Okay, so it's like a soup can, right? And we want to use the least amount of metal. So metal, so like we have a metal can, and then we want to, it's like if I use more metal than I need to, then it's going to cost me more, which means my profit when I sell it is going to be less, right? So I want to use the least amount of metal for a fixed volume, right? So my goal, really, what this means is I want to minimize the surface area, right? So what I'm going to do is I'm going to draw a picture so I can visualize what I need to do. So here's my cylindrical can. Remember, when we do these, right, this is based on a radius and a height. Okay, so I've got this, you know, certain radius and certain height. We don't know what's going to happen with the radius and height. That's actually what we're going to be solving for. So let's start figuring out our variables. We're going to choose our variables. Okay, and let's see. So basically, when I deal with surface area and volume and my cylinder, what I'm dealing with is my radius, R, my height equal to H, right? And I've got the volume and I have the surface area. These functions will rely on our radius and our height, okay? But these are the things that we're going to use in our step 2, which is our function. Find our objective function and the interval of our input, right? Okay, so let's think about, we want to minimize our surface area. So that our question tells us, so our surface area. All right, so I have to think about my surface area. So I've got a circle on the bottom and a circle on the top. Okay, so my surface area is going to be the area of the top, which is pi r squared, plus the area of the bottom of the can, which is also pi r squared, plus now if I, what's this, you know, the surrounding area. So think about it like if you've got a soup can, you cut off the label, you open up the label, it's a rectangle, right? So it's a rectangle whose length has to wrap around a circle. So the length of that rectangle is the circumference of the circle. Side. So 2 pi r is our circumference, base times height, right? So this is our base, 2 pi r times our height. Okay, so let's put it all together. So our surface area, I'll call it A, is pi r squared plus pi r squared, 2 pi r squared plus 2 pi r times h, 2 pi r times h. Well, now I have 2 variables, right? I've got the radius and the height, but I want my area to be in terms of only one variable. So let's go back to our volume. Right, so we were given the volume was 900 cubic centimeters. It was a fixed volume. So volume on a cylinder is basically your area of your base times your height, right? So when I go to do that, that's going to be area of the base pi r squared times the height. Okay, that gives me an equation for the volume. Now I get to choose, do I want to solve height in terms of radius or radius in terms of height? It's going to be up to you to make that decision, okay? Personally, I kind of look at it like, well, if I solve for height, then I'm going to get 900 divided by pi r squared. Okay, that's not so bad. If I solve for radius, right, I'm going to get radius equals 900 divided by pi times h. Then I have to take the square root. So it's up to you which one you want to work with. Personally, I'm going to leave it like this. I don't have to take any square roots. I don't have anything, you know, kind of hanging around that I need to worry about more. So now what I'm going to do is I'm going to take the h and I'm going to plug it into here. So then I have my surface area function in terms of only one variable. So my surface area in terms of my radius now, 2 pi r squared plus 2 pi r times my height, 900 divided by pi r squared. Clean it up a little bit. So my area function, surface area function, 2 pi r squared plus 2 times 900, 1800. The pi's cancel, one of the r's cancel, and I'm left with that. So there's my function. That's the thing that I need to optimize, right? And then the interval, let's think about it. Well, we know it has to be greater than 0. But we weren't given any other information about the rest of it. So R can be as big as we want. It won't make a lot of sense if R is like super big, but it can be as big as we want. So that means that my interval is basically, I can't include 0 because, right, I've got this divide by 0. So my radius can't be 0. But my radius is basically, it's unbounded, right? I can go from 0 to infinity, okay? Even though I can't actually touch either ends of those endpoints. All right, so step 2. So step 3, we want to optimize. Right, so we were told when we go to optimize this that we want to minimize. We want to look for a minimum on our critical point here. Let's go ahead and think about that. So let's go ahead. We'll do the derivative first. So area is a function of r. So I'm going to take everything is with respect to r here, right? So when I go to take this derivative, right, I've got 2 pi is my coefficient times the exponent. So I get 4 pi times r, right? Now this 1800 is my coefficient, 1 over r. I go to take that derivative, I get minus 1 over r squared. So this is 1800 over r squared. As a power rule. Set that equal to 0. And I'm going to solve for r. I'm going to get r cubed, 3. R cubed equals 450 divided by pi. I take the cube root, and that's approximately r is equal to 5.23 centimeters. Okay. All right, so let's just visualize, right? We said this is an open interval, so I'm just going to draw out a little graph here. Here's my surface area, function a sub r. Oops, sorry, you can't see that, as a function of r. So now, right, I'm going to think about, I can't just, you know, look at my boundaries, but I can take the limit. So the limit, right, the limit as r goes to 0, right, of my surface area function, my area r. So the limit as r goes to 0 of my area function is going to give me, as r is going to 0, where am I? Here. As r goes to 0, my area function, so this term's going to dominate, this thing's going to go to, right, this thing doesn't exist, my pen's dying here, hang on. Okay, then I can think about my limit as r goes to infinity, my area function, right? So this thing here, as r goes to infinity, this thing, right, goes off to infinity here. So basically what happens is, we're looking at a function, it goes like this. If I were to plot this function here, this is what I'm looking at. It kind of looks like a wobbly parabola. It's not a parabola, but it kind of looks like a wobbly parabola, right? So what happens is, right, as r goes to 0, this term dominates, right? So we would say, as r goes to 0, our area function goes to infinity because of our 1 over r function dominates. As r goes to infinity, area function goes to infinity because our r squared term dominates. That's kind of how you're thinking about it, right? Which term on here is going to be dominating. So this is our critical point here. It minimizes, right? So basically our critical point gives us a minimum. Okay, so roughly speaking, right, let's go ahead and solve for our h values. So if you have r equals 5.23 centimeters, our h is equal to, remember, 900 divided by pi, oops, sorry, can't see that, pi r squared, 5.23 squared. So my h is roughly going to be 10.46 centimeters. H. Look at that, 5.23 for radius, 10.46 for our height. So roughly speaking, right, roughly speaking, if the height is twice the radius, we can minimize our surface area. We'll minimize our surface area. Okay, that's kind of how you want to be thinking about it. Right, so you notice I couldn't actually just plug in my boundaries because it's an open interval, right? But I can kind of think about it in terms of a limit. And what's actually happening. I don't even really need to do this, but it kind of will help me conceptualize what my graph looks like. This I can also just plug into my graphing calculator, and I'm going to get a graph that's shaped something like this too. But conceptually speaking, this is what's happening. 1 over r term dominates, or r squared term dominates. Okay. So optimization. I have one more example, but I'm going to save it for next time so that we have time to go through it without rushing. Also, I think there's a lot of stuff here. And I want it to kind of sink in, give you guys a chance to kind of think about it before we, you know, finish up our last example and then move on. So Wednesday, we'll finish up this last example. It's based on this problem right here. And then we'll talk about chapter 3.5, which is L'Hopital's rule. 3.5 will not be on our quiz on Thursday. But Appendix A and 3.3 will be on our quiz on Thursday. And on Wednesday, we can talk homework problems too. If you guys have questions, please come to class with questions on chapter 3.3 so we can work it through. Okay. Okay, guys, have a great day, and I'll see you on Wednesday.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.
Bye-bye. Take care.